Hello, Matthews Gatos here. Welcome to this video for lesson number 2, polynomials of degree 3. So in our last lesson, we looked at polynomial of degree 0, 1, and 2. Let me introduce you to the cubic function, which is a polynomial of degree 3. So you can see these look kind of like I took a degree 2 polynomial, parabola, with a degree 1 polynomial, linear, and kind of mash them together. So it kind of looks like here's the polynomial degree 2, and then we also have that kind of line part of degree 1. So you look here, here's that kind of like curving point here and another curving point here. So it's kind of like those two properties put together. And in fact, the properties of cubic have properties that are similar to quadratic properties and also linear properties. The one thing that I want to point out first is this end behavior. And if you look at the end behavior of this graph, it's very similar to a linear function. The arms point in opposite direction, and they're going from quadrant number 3 to quadrant number 1, similar to a linear function with positive slope. They're also similar to degree 2 polynomials in that they have a max and a min. We call it a max turning point or a minimum turning point. The reason we call it that is because it's not a true max or min, because those arms go in opposite directions, so there's really no high point if I go off to positive infinity, and there's really no low point if I'm going down to negative infinity. So we call them maximum turning points, minimum turning points. Another way that we call them is a local max or a local min. So we can also call them local max or local min, which just means in that area they are a max or min. So here's an example here where I'm labeling local max, local min. So it is a maximum turning point, but I can also call it a local max. This is a minimum turning point, which is also called a local min. Now this cubic function here does not have a local max or a local min because it's always increasing. At this point here I'm increasing and I clearly go down and then I clearly go up. This one here is always increasing. So this little change here, it's a curve change. What I mean by that is it looks like it's going to be a curve that's going down, and then it looks like it's a curve that's going up, and right in the middle is where they join. That's called a point of inflection. So you can kind of think it almost like a slide, and at that point there it's called a point of inflection. So let's look at these polynomials. We're going to graph them and we're going to see the different properties that they have. So I have 3 different polynomials that are cubic functions. I also have them in factored form, and I've graphed them using this window setting, and here's what they look like. So we want to talk about how these graphs are the same and how they are different. But what I do want to point out right away, I noticed my y-intercepts. So if you look at over here, this one has a constant value of 5 and a y-intercept of 5. Constant value of 4, y-intercept of 4. Constant value of 3, y-intercept of 3. And then we can also look at the factors. So see how the blue one has two factors? It only has one y-intercept because this is unfactorable. So I can't factor that any further. But look at the red graph. See how it has 2 factors? The red graph has 2 x-intercepts. And look at the green graph. And it has 3 factors and it has 3 x-intercepts. 1, 2, and 3. Okay, let's look at this in a little bit more detail. So I want to talk about how these are the same and how they are different. So here's some of the ways that they are the same. They all have the same domain and range. Because these arms extend infinitely in both directions, I am going to cover every possible x and y value. Okay, these graphs all have 2 turning points. So they have a maximum turning point and they all have a minimum turning point. They all share that x-intercept at 1 because they all have that factor of x plus 1. They all have one y-intercept, and every linear function, quadratic function, or cubic function will have a y-intercept. the left arm is down, the right arm is up, so similar to the end behavior of a linear function, and they all have local maxes and mins. So that's how they are the same. They're a lot more same than they are different. So let's look at how they are different. They're different in that they all have different number of x-intercepts and they occur at different places. They all have a y-intercept, but they're all different values, and they all have different max and min values. Okay, so we already talked about this, but let's formalize it. How can the number of x-intercepts be determined from the fully factored form? Well, the number of x-intercepts is the same as the number of zeros, the number of roots, the number of solutions, the number of factors. That all means the same thing. The value of the x-intercepts can be determined by doing opposites. So the opposite of a +1 is that -1. So that's why they all intersected at -1. And then, oops, if you look at, oh, Bob's paying us a little visit here, my little smartboard ghost. There we are. Okay, let's try that again. Okay, so this one here was unfactorable, so it had no more x-intercepts. This one here, the opposite of a -2 is a +2. So you can see I have a x-intercept there. And the opposite of a -1 is a +1. And the opposite of a -3 is a +3. So I can see the x-intercepts by doing the opposites of the factors. Okay, so I want to look at a whole bunch of different graphs, and I want to see some of the things that are going to come up over and over and over that are the same. So I've graphed all of these ones here for you. You can draw a little sketch of them, and let's talk about all of the properties. So because these arms of the graph extend infinitely in both directions, they're going to cover all possible x values. So they all have a domain of the set of x such that x is an element of the reals. Similarly, they also have that same range. So this is going to be true for every cubic function. Okay, let's talk about the number of x-intercepts. So this blue graph has one x-intercept. This red graph has one x-intercept. And this black graph has 1, 2, 3 x-intercepts. Okay, let's focus on the number of y-intercepts. So they all have one y-intercept. The y-intercept, all of these here, is at the constant value. So this one has a y-intercept at 0 because there's no constant value. This one has a y-intercept at 0 because the constant value is +0. This one at -20 because it's doing -20. Okay? So what we're trying to do is if we look at a bunch of these, we're trying to see if we can find something that all cubic functions have in common. Okay, number of turning points. So this function here in blue is always increasing, so it has no turning point. It has a point of inflection. This one here going down, this one's always decreasing, so it also has no turning point. Okay, for this one here, you can see I have a maximum point. I turn around and have a minimum point, so I actually have two turning points, a local max and a local min. Now let's talk about the end behavior. So the end behavior of the blue graph, the left tail is pointing down, the right tail is pointing up. That is because I have a positive leading coefficient. The red graph, the left tail is up, the right tail is down. That's because I have a negative leading coefficient. Over here, my left tail is down, my right tail is up. I have a positive leading coefficient. That's why it works. So I'm starting to see some things that are in common with these, but I want to look at some more just to be sure. Okay, so domain and range, we agree. It's going to be the same for all. So that's definitely something they all have in common. But let's continue on here. So this blue graph here, it has two x-intercepts. The red graph has 1. The black graph has 3. So it looks like I'm seeing 1, 2, or 3. I'm curious if I'm going to see an example where there's 0 x-intercepts. Let's look at the y-intercept. So here I have no constant value, so it's a 0. It's like a +0. Here my constant value is -6. So that's my y-intercept. Now my last graph I have a +2. So that is my y-intercept. Okay, number of turning points. So this one here comes down and turns around and comes back up. So it looks like it has 2 turning points, local max and min. This one here also comes down and and has a local min, turns around, has a local max. It has 2 turning points, and so does the last graph. Okay, let's talk about end behavior. So the end behavior for this one here, left tail up, right tail down, because I have a negative leading coefficient. Actually, they're all negative leading coefficients, and if you look at that, they all have the same end behavior. Okay, let's look at just these last 3 here, and we're going to tie it all up together. So again, they all have the same domain and range. Okay, so for this blue graph, I have 1 x-intercept. For this red graph, I have 2. And for this black graph, I have 3. So it looks like I'm not seeing a graph with 0 x-intercepts. The y-intercept, again here, constant value of 7. This graph has a constant value of 14, constant value of -5. Okay, this one here is always increasing. There's definitely no turning points. So just a point of inflection. This one here has a local min and a local max, so there's 2 turning points. As this one here, the black graph, local max, local min. Okay, so all of these graphs here, let's look at the end behavior now. So positive leading coefficient, left tail down, right tail up. Negative leading coefficient, left tail up, right tail down. And this one, positive leading coefficient, left tail down, right tail up. Okay, so I want to put this all together because I've seen now 9 graphs. So all of those graphs have the same domain and range. X is an element of the reals, Y is an element of the reals. All of those graphs had 1 y-intercept. They didn't have 0 or 2. It's always going to be 1. Okay, now the graph of a polynomial degree 3 either had 0 or 2 turning points. I didn't see a graph with 1 turning point. If I have a graph with 1 turning point, that's a quadratic because it has a max and it turns around and goes back down, or it has a min, it turns around and goes back up. And we saw that they have 0, 1, 2, or 3 x-intercepts. No 0 x-intercepts. The reason is the arms extend in both opposite directions, so you're going to cross the x-axis at some point. Okay, let's talk about the end behaviors. So if the leading coefficient is positive, then the right tail of the graph goes up, the left tail goes down. Similar to a positive sloping line. Similar to that. Okay? If the leading coefficient is negative, so similar to a negative sloping line, then I see that my right tail this time goes down and my left tail goes up. Okay, let's talk about the behavior of the graph from left to right. So looking at this graph here, let's look at the end behavior. If a graph starts in quadrant 3 and ends in quadrant 1 like this, then I know that the leading coefficient is going to be positive because it's like this kind of a sloping line, positive. If the graph starts in quadrant 2 and ends in quadrant 4, it's kind of like a negative sloping line, then I know that the leading coefficient is negative. So I've said this before, but let's formalize it now. The end behavior of a cubic function is similar to the end behavior of a linear function. So it behaves just like a line. Okay, so let's do an example here. So in the last question, part 3, students were asked to graph this quadratic using the set window setting. Kevin entered one of the digits incorrectly into his calculator and accidentally graphed this one instead. So you can see he entered in a 20x squared instead of a 10x squared. How can he tell the graph displayed on his calculator does not show all the main characteristics? Because see, look, this is all he ended up getting. Okay, so well, that kind of looks like a quadratic function. Okay, so I know that it's not a cubic function because it looks like the arms go in the same direction. Another reason is that I don't see, well, actually, I would say that's the main reason, because I should either have a point of inflection, a local max, or a local min, and that's because the arms go in opposite directions. So I only see one turning point. So remember, your choices for cubic are 0 turning points or 2 turning points. So I definitely know that I've made a mistake. So writing a graphing calculator window that's going to show all of these. So if I wanted to see, even though he entered in that wrong, it still should look like a cubic. It's just his window setting is off. So I really adjusted my window setting, and then you can see that this part of the graph is what he was seeing here. So you had to expand your window and make y quite a bit bigger to see this part of the graph here. Okay, so just knowing something about your polynomials when you graph it is definitely going to come in handy. Okay, so the last class example is a thing about window setting. It really comes down to the window setting. So I want to give you something that's going to help you with the window setting. If I go into the table of my calculator, because in the last question I could have just guessed and checked a whole bunch of times until I found the right window setting, or I could be smart about it by looking in the table. So what I did is I looked in the table from 0 to 10, and I see that these numbers here are always increasing. So that really doesn't help me, because it's like over here, the ends of the graph are always increasing. So I'm not going to see a turnaround point, because the turnaround points are down here and here. So then I looked at my negative values, and looking at my negative values, I can see that I start really small at negative 213, but I'm getting bigger and bigger and bigger. So I definitely have a turnaround point. Okay, so I'm going to look for that area that I have a turnaround point. So see here how I'm coming up 247, 247, and then I go back down. So these ones here I'm increasing, and then at this point here I'm decreasing. Okay, so at that turnaround point, that's going to help me set my window setting, because what I'm going to do is I'm going to have my y max value be my turnaround value. So I know that my maximum value would be 247. And then I know that my x maximum value for my window setting would just be double the turnaround value. So see here how I'm happening at -7 and -6. I know that my x, I have to go all the way down. Now because this is a minimum, it's a negative, I'm going to say my x minimum value here has to be double the turnaround value, which in this case here would be -14. So I need to make sure that my window setting goes all the way up for y to have a maximum at 247, and all the way down for x to be at -14. Okay, so in your notes, you guys have this really nice summary of all of the characteristics of a polynomial function. I won't go through and read that, but I just want to note that we want to use proper set notation for our domain and the range, and your workbook doesn't use that. So definitely make sure that you update that. But you guys can read through and see all of the characteristics all together of 0, 1, 2, and degree 3 of polynomials. So this concludes my study of polynomials. You guys can go ahead and do the assignment, and I'll see you for the next video.